start?
Wow, well, thank you so much, Dr. Strickland, for that amazing talk and sharing some of your experience at the Nobel Prize ceremony. Now we're going to have our fireside chat. As I mentioned earlier, this is going to include some questions that were submitted in advance from our audience. And if you do want to share this portion of the event on social media, feel free to use the hashtags #UWaterlooProud and Nobel Prize. So, Dr. Strickland, I have some questions here from the audience, and I'm going to start with one that was submitted from Stuart Lamont of Kitchener. Now, these are his words, not mine. He's asking, when you were a wee girl, did you want to be a physicist? And I think we're all curious to hear how you got into this field.
Depends how the wee girl would be, I think. I remember, actually, my parents had this beautiful clock. I don't know if my sister remembers this beautiful cut glass clock beside their bed. I don't know what possessed me, but one day I thought, I want to see how that clock works, and I took it apart. I had no problem taking it apart. I had no way to put it back together. I was pretty wee. I think I got in a little bit of trouble. So that was the first time I tinkered. I don't know that I tinkered a lot. My dad loved to. He had a workshop down in his basement, and he liked to tinker with things, and he was an engineer. But I just, probably right from grade 1 on, I knew that I liked math and science, and so in that way, I probably knew that I would be in math or science.
And I think I heard you liked Legos as a kid, too. Is
Love
that right?
Legos. It's a great toy. I think, you know, we used to have, I'm sorry if you're young, because it's Lego, I'm sure it's still a fun toy. I still let my kids play with it. But we used to get giant boxes of it, and it was really about making buildings and stuff. And now they're all very specific to do very specific things. It's less creative. You sort of follow a program, whereas we were just given boxes and boxes of Lego to do whatever we wanted with.
And so you're from Guelph, Ontario, if I'm right. And from what I understand, as a child, you also visited the Ontario Science Centre and were kind of exposed to science through that way. Is that true?
Well, that's according to my mother. I don't actually remember, and yet I must have been 10, so that tells you how bad my memory is. I do remember going to the Science Center. I don't remember quite the story that she liked to tell, because other people would ask why I wanted to study lasers. And then she would say, Donna, it's your dad. He, you know, when we went to the Science Center, he saw the big laser that was there. It was a CO2 laser. And he said, come on, we have to see this. This is the way of the future. So what I remember is when I was trying to decide where to go to university, and I saw McMaster had a program in lasers and electro-optics. It was a gut reaction. I just thought, lasers, they sound like so much fun. How cool would it be to work with lasers? And so that's why I went to McMaster, because they had a laser program.
Actually, that's interesting, and lasers are something that many of us are exposed to through movies and television, for example. Are there a lot of kind of pop culture references that come up when you talk about lasers, and is that, I'm assuming, what most people know about lasers comes from movies like Star Wars? Do you get a lot of questions about that?
Yes. And you have to remember that I thought lasers were cool without ever, I guess I saw one at the Science Center, but they weren't around like they are today. This is back in the 70s, right? They were simply research tools back in the day. A couple of summers ago, I worked here, we didn't work, I volunteered once a week and showed the children in the Engineering Science Quest Camp a laser and how to build a laser. And of course, they always wanted to talk about those lightsabers. There's another picture of Gérard and I. They gave us one at one of the 3 balls we were at and made us fight each other. You know, I have a problem with that because, of course, the light comes out in all directions, which means it's nothing but a light bulb. And so there's nothing special about it. How come people think that's so special? No, it's just a giant light bulb. Maybe the electricity could kill you, but otherwise the light's doing nothing.
Well, I think for me, one of the most fascinating parts of your talk was learning about how, or the science that went into chirped pulse amplification and sort of how you and your collaborators came up with that. So I was wondering, and this is also a question from the audience, if you could tell us a little bit about the struggles and challenges behind that work. I'm sure there were many, but what were the struggles that you recall and how did you overcome them?
Well, before we did CPA, I was trying to take a 30 picosecond pulsed YAG laser and focus it into something called carbon disulfide and sulfur, you know, the rotten egg smell. And we were trying to focus it in, and then it would turn black and ruin it. Now, since then, actually quite recently, people are studying, the nano is all the rage right now. And actually, it was actually nano black carbon that was coming out of the carbon disulfide because we were hitting it. But at the time, we didn't know what that was. It was just a pain to have those black things, and then I would have to clean them up, and it was the rotten egg smell every time I had to change that out. So the experiment didn't work, and really I was glad to not have to do that one anymore. But while I was struggling with that, and before really Gérard had talked to me about CPA, although he had the idea back in '83, people did come up with fiber pulse compression. And so people were figuring out how to turn 100 picosecond mode lock YAG into single picosecond pulses. They weren't thinking about the amplification, they were just trying to get the 100 pico down. And so along the way, they realized that you really need to do the stretching. You didn't want just long enough to make the colors. You wanted to have a nice linear sweep of the colors, which the self-phase modulation did not do. It actually made an S-shaped thing. And so you couldn't compress an S-shaped thing. But if you let the colors separate out, then you had this nice linear one. And then the Tracy pulse compressor had been known since '69. So they knew they could put it back together if they could figure it out. And so all the pieces, in a way, just sort of fell out in 1984 for us. And we went, OK, now we know how to do the stretching, and now we know even how to get the bandwidth, and now we know a few of these things.
And what was your reaction when you accomplished this? I mean, do you have any sense of what a big deal it would go on to be? Was it sort of like a eureka feeling? Or
Absolutely, absolutely. Yeah. I will say that I always will remember the night that we had with Steve. I mean, Steve thinks I give him too much credit, and because he only worked one night and I worked for a whole year. And that's why he wouldn't have his name on my I put his name on the paper, but he took it off. But he said, you worked really hard for this, right? But he was there with me when we were jumping up and down, going, it works, it works, it works. And Marcel Bouvier, who I had his name up there, but I didn't give him credit, he was the electronics engineer. And again, not only did Gérard beg and borrow to get the fiber, he begged and borrowed and got an old glass laser system that was very old and needed a lot of work by Marcel. And in fact, my husband it was called a Quantel, and he somehow put up the new sign and called it the Marcel. After a while, it was just, he had done so much work for me. And it turned out that was a Thursday night I worked with Steve, and on the Friday was his birthday. So I went to Doug's and my favorite dessert place, Crème de la Crème, and got a great big orange cake. And Gérard went and got the champagne, and we knew it was big, and we had a party.
That's amazing. Now, I have to ask, because we're on the subject of struggles, you mentioned the optical fiber that you guys had, and you ended up with, yeah, so how did you react when that happened? Was it a disaster, or did you know it was going to be okay?
A mini disaster, but only a mini one. We pretty much, we're an experimental group, and by the end, we were a pretty big group, and there was one student who worked for 8 years. Now, he was sort of periphery to our group. He was working with using one of the lasers, but he hadn't broken anything in the whole 8 years. And the rest of us would say, you're not really trying hard. If you're being so careful that you never break anything, you're not, and Gérard wanted us to move, move, move. We had to move, move, move. So I will say that Gérard would have never yelled at us for breaking anything, because he also wanted us to move, 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 and accidents happen. Luckily, it would have been a disaster had 1.4 kilometers not been long enough to do it. We did only stretch to 300 picoseconds, and you really would have liked a nanosecond, but even the 2.5 kilometers wouldn't have gotten us quite there anyway. But it was long enough to show that the thing worked. So.
Wow. And now I know, as mentioned in the introduction, you were the first woman to win the Nobel Prize in Physics in 55 years, and I know you've answered this question a lot. We've seen 3 women win the prize ever. You're the third. Congratulations, that's a phenomenal accomplishment.
Thank you.
We still have a lot of conversations in this country about diversity in science and physics, women and people of color and representation. So I'm really curious to know how that's changed over the course of your own career, and what efforts you see for the future to bring in more diversity into the science community.
Well, I think for women, it certainly has changed. It's not changed a lot, okay? Back in my day, it was about 5% women in the PhD physics category. It's up to about 15 to 20% now. So it is moving in the right direction. It's just going to take a little while to get there. But I also think that, I've watched at the same time, I was at McMaster, one of my very good friends went into medicine and on into surgery, and she complained about it being a male bastion of whatever. And yet, in that same time frame, it's gone to more than 50% women going into the medicine. So to some extent, whatever the battles are, the women were willing to do it for medicine and not for physics. And I personally think it's because society doesn't care that much about physics compared to medicine. Most parents tell their kids, you want to be a medical doctor, you want to be a lawyer, because those are the good paying jobs, right? Most parents aren't going, you really want to be a physicist because you can get a mediocre paycheck. Maybe good to mediocre, but not, compared to a medical doctor, right? And also, everybody says, oh, you're not really a real doctor, So I think that's what it will take for that. I think people of color, still are struggling more. And I've said other times that when I was doing it, people would say, way to go, you're trying to make it in a man's world. And I had more people cheering me on than really putting me down. But one of my good friends in the ultrafast community is a black man. And he got a great job at Bell Labs after, well, he actually did a postdoc there too, but then got to stay on. And so, I'm sure he thought he'd died and gone to heaven. My husband Doug got to go to Bell Labs, and that's what he thought. And the first time he went to a meeting, though, as a black man, when he came in, the other men thought he was at the waiter and asked him to get the coffee. And I heard that, and this would have been in the 80s, and I'm thinking, what the heck is going on here? And there's still very few people of color going in. So I think there still needs to be a lot of work done for that.
Mm-hmm. As a follow-up question this is from Erin Meager from Ryerson. She's asking, how, in your opinion, can we as a community encourage more women and girls to pursue and succeed in science?
Well, I think, personally, I think people should do what they want to do. I think everybody should be encouraged to do what they want to do. So I don't know that I like the idea of encouraging people to do A, B, C, or D. I think people should be encouraged to figure out what they're good at and then say the world's yours to pick and choose from. Mm-hmm. So I think what we want to do is expose everybody to as many different things as possible, because how do you know what you're good at until you've tried as much as you can? So I would like to see that, and I would like to see every field being open to both genders. Mm-hmm. Because if we swing too far one way, we tend to forget on the other side. And I would like it to say that everything should be wide open for everybody.
Mm-hmm. Absolutely. So one of the things I wanted to ask you about was the importance of fundamental science, basic research for research's sake. In this lecture and in a lot of the news coverage around your work, we hear about the applications of this technology, which have been huge, from laser eye surgery. That video, by the way, was very hard for me to watch, but fascinating, to industrial cutting and other techniques, and even future applications in physics research. But you're a scientist, and what are the benefits to being able to just kind of follow your instincts in the lab and not really maybe worry about the end product, the end result, just science for science's sake? Why should we as a society be investing in that and really care about it?
The point is, we can't keep coming up with new applications if we don't keep having better understanding of the world around us. And so, when I mentioned Einstein is the one in 1917 who laid down the laws for the laser. He is the one who wrote the equations for absorption, stimulated emission, and spontaneous emission, the three processes that go on in a laser. So that was 1917, and yet we didn't have a working laser until 1960. It takes a long time, and it takes a lot of people. It wasn't just Einstein and then everybody else doing nothing for 50 years. It is an amazing amount of work that goes on in between having that idea and the laser. And then when the laser came along, all of a sudden, it showed that you could have these nonlinear effects, which we use in umpteen different ways now. But if somebody hadn't invented the laser, we wouldn't have understood you could have these nonlinear effects, right? Well, of course, Maria Giffenmeyer thought them up without even seeing it, but nevertheless, we couldn't have them. And again, CPA came along, and not because we were trying to do new eye surgery. I was just trying to see, can I get an atom to absorb 9 photons or not? Mm-hmm. And we came up with the CPA laser. And then it showed that actually the way we thought it would interact with matter is not the way it interacted with matter. And we had to rethink again, how does light interact with matter? And it was from that understanding that a whole lot of new things that came along. Some of them are the applications. But my postdoc supervisor, Paul Corkum, everybody thinks he'll win a Nobel Prize for his work in attoseconds. But he took the new understanding that we had of the fact that the light moved these potentials over and out, and that the electron would go out and be accelerated and come screaming back. he realized that was the reason people were now seeing not the 9th harmonic, but at the same time I did CPA, people started to see the 105th harmonic. It was just crazy. Nobody understood why. And the first paper says, we don't know why, but it has something to do with it being almost the same power as a multiphoton ionization power. And so he now can make attosecond pulses, which are fast enough and short enough that he's now watching how electrons move. We did, with our picosecond, we could sort of watch how atoms move in a molecule, but he's now watching how the electrons are moving in an atom. And so from that, new applications will come along again. But each step of the way, it takes technology, and it takes pure science, and it takes applications. And you have to have all of them and keep working together to keep it moving forward. But if we stop doing fundamental research in 20 or 30 years, we'll run out of the bank of all these ideas, and it'll be hard to keep moving forward.
And when you first conceived of and worked on your laser hammer, the CPA, did you have any applications in mind, or was it just pure curiosity?
It was just to do this idea of could we make a high order harmonic generation. That was all we were after. We just thought, you know, is it possible? People had seen 3rd and 5th order, but people hadn't seen beyond, and we wanted to know, could it be possible if we turned the light up that high?
Wow. Now, do you think here in Canada we do enough to support our researchers and scientists in their work, their sort of basic research?
Well, of course, everything swings back and forth and back and forth. A couple of years ago, we had a report called the Naylor Report, and one of the people that sat on it was our previous physics Nobel laureate, Art MacDonald. And I think it did help convince the federal government that they were putting too much emphasis on industrially relevant research. And we had to sort of go with hat in hand to industry saying, you know, we want to do research, but will you support us too? Because the government will only support us if industry supports us. And a lot of that is short-term research, and it's not the long-term where you let a student think about it for a few years and over the whole course of a PhD, flesh out an idea. And so that was one of the big pushes for the Naylor Report to say, as a country, we have to support discovery-based research. And so it is somewhat swinging back. It's not like some of the other countries in the world. There are other countries in the world that support it big time.
I mean, I think one thing that comes across when you speak about your research is how much you enjoy being in the lab and doing this kind of work. You know, your curiosity and your drive to answer some basic questions about how the world works. So I have to wonder, having won the Nobel Prize, your life has clearly changed a lot in the last few months, and you know, the next year or two, I imagine you'll be pulled away from the lab quite a lot for events like this, for which, you know, we're very grateful to hear your thoughts. But nonetheless, how will you cope with being out of the lab? Will you miss it? How is your life going to change?
Well, I will miss it. I usually, when I'm here, and I usually try to be here a lot, is I'm in the lab about 5 times a day, you know, seeing how it's going, and I quite often still tweak the lasers. I still can tweak any of the lasers in my lab and make them work myself and watch the experiment. There's some of the experimental apparatus that the students have built, and if they've built it, I don't touch it. That would just be a rule. No supervisor should touch equipment built by a student, because we would destroy it. But yeah, I think I will miss that. I will probably have to try to get a postdoc or 2 into my lab somehow. I will have to find funding for that. And so they can actually run the lab, because I don't think it's right to just leave the students totally unattended. And I will be traveling more than half of the time in the next year to 2.
And what are your goals over the next year or 2? I assume communicating your research to the public, events like this, and what do you hope to accomplish now that you are a Nobel Prize winning scientist?
Well, one of the things that winning the Nobel does give you a big voice, and one of the public policy things I'd been working on with OSA, the Optical Society, was to try to convince governments of the importance of photonics. Photonics people will say that electronics was the technology of the 20th century, and we believe photonics will be the technology of the 21st century. And that's because light travels faster than matter, and so it can travel faster than electrons. And so as we speed everything up, it will be done with photonics. So when we thought as a society, how do we want to convince all the world's governments to do that, and not just the US, because it is a US-based society, although it's an international society, the Paris Accord had come along, and we thought, well, okay, photonics can actually help measure, are you making changes to the environment? Are you doing what you say you're doing? And also, even if you're doing it, is it making an effect? And so we wanted to reach out, and I said, I want to get to my Canadian government and make this point. And a little over a year ago, we had a meeting, and we couldn't get anybody from Environment Canada to come to our meeting. And one of the things they said, well, we're so busy answering the commissioner's report. And in the commissioner's report, it said, you know, one of your problems is you have no way to measure if you're doing anything. And we were sort of screaming, well, that's why we want you to come to our meeting, because we want to tell you how we can help you measure it. And it isn't that we have all the answers. We are asking. This is one of the times that we're saying, you come and tell us what the applications are. What is it that you need to measure to know what you need to know for the Paris Accord? And we'll go back and see, can some of our photonics ideas work for that application? So then, the next meeting that we were going to have, and this time I thought, I'll just have the scientists get together, from the people that do the environmental measurements to the spectroscopists to the technology photonics widget people over here and the standards people to know it's a good measurement. We'll gather them all together and see, can we come up with a unified voice to then go to the government. But as soon as it was known that I was going to be there and speaking at it, and this is just a month after winning the Nobel Prize, not only did the VP of NRC show up because it was at an NRC that we were having this meeting.
Being the National Research Council?
The National Research Council, but the Deputy Assistant Minister for Environment Canada and Climate Change, a scientist, came to the meeting, spoke for half an hour, and she was just so excited about what we were doing. And I will go back and speak at an Environment Canada meeting now in February 27th. She's invited me to come and speak to their meeting to tell them what photonics can do. So it has helped to get a Nobel Prize to have people want. They all of a sudden think I know what I'm talking about. So.
Well, that's fascinating. I mean, when we talk about Environment Canada, what are some of the applications there? What kind of research are we talking about?
Well, of course, one of the great things we're doing, and this is not my own field, because so far I don't think anyone's using CPA lasers with it, but I learned something at the meeting from a year ago. There's a big program at Laval on the Arctic. And because we have the Arctic here in Canada, and it's warming up faster than any other part of the Earth, we have to worry about the Arctic. And one of the things that's happening is that we're losing our permafrost. Mm-hmm. And what's the problem with losing the permafrost is that most of the transportation up there counts on the ice to keep the roads, or the runways to have, you know, when the ice roads aren't there, they have to fly in, but then you still need a good landing strip, and they're buckling because now the permafrost is there. So we're putting in optical sensors in the highways, on the runways of the airstrips, and that can detect all the stresses and strains, and so we're watching that, and we're using photonics for that. But there's also photonics in planes that fly over gas-leaking things out west, you know, and measuring to say, you know, is the methane that's coming out of there what they say is coming out of there, or are there more leaks than they don't know about? And of course, just at the meeting a year ago, a scientist was there to show that it's 50% more than what they think. And it's not where they think it's coming out, but they can now spot where the leaks are. And the companies want to know this because this is something that they can fix and want to fix and don't want the leaks. So
that's fascinating. Are there any other applications or future research in this field that you're particularly excited about? I mean, where are we headed next?
In CPA or in environment?
Let's say in CPA.
Well, I think the one that I would like to watch the laser acceleration. I don't know that I would work on it myself because it requires pretty big lasers. But I think that's one that holds a tremendous amount of promise, both for medicine, and of course, if you do medicine, you're more likely to get tax dollars because taxpayers are willing to pay for medical research more than pure physics research. But you should want to do it all, okay? But Gérard had me join him at CERN, where he is trying to convince the people, don't build an even bigger tunnel. Try to put a bunch of petawatt lasers in there and do laser acceleration. It's a lot of years away. It's going to take a lot of engineering. But I think there's some really fun, neat ideas where they're thinking about, because they need to have more rep rate. These really big lasers only fire about once an hour, so you can't do that at CERN. Fiber lasers, on the other hand, have a lot more average power, but none of the peak power can be very high, because otherwise you're blowing up your fibers. There's people that are working on how to take 1 million fiber lasers and phase them all together so that they can add up from the million of them to be one giant pulse at the end, and those pulses will come at 100 kilohertz, so it'll be a tremendous laser. So, but they're talking about, you know, moving space junk out of the way because of the pressure of the light beam in these lasers.
So you could zap space junk
zap,
around Earth?
like all of those too many satellites that are up there doing nothing anymore. They're just in the way of the other satellites. There is a lot of pressure. Like, I do sometimes, although now I'm being more careful, when high school students would come in, I would let them be slapped by the pump lasers, right?
Wow.
Not the short pulse ones, but just the pump ones. And you really do feel like you're being slapped. It's hard, you know, with this type of light, you don't feel it, but you really get slapped by these shorter pulse lasers. And so you can feel the momentum. And so that is the idea, that it would kick the space junk out of its orbit, and then it would blow up.
That'd be very useful, because I know space junk is a massive problem,
It's a
actually.
massive problem.
For sure. Now, I have one more question for you. It is a little unusual, but I think it's an interesting one. It's from a 10-year-old, possibly a member of our audience, Justin. So he wants to know what would happen if you took Dr. Strickland's strongest laser in the world and shone it on a solar panel. And he asks, would it make enough energy for some of it to go back into powering the laser and still have more left over to make more energy through the panel? So basically, if we took the strongest laser in the world and we zapped a solar panel, would we have
I know, I like how
free
he calls
energy
it Donna
forever?
Strickland's largest laser. I don't own the largest laser by any stretch. Okay, so there's a few things to take note here. Is, as I said, these laser pulses only come, the biggest ones only come maybe once an hour. And the pulses are only a picosecond of pulse. So the peak power, which is energy per unit time, is huge. It's as big as what's on the entire US grid. And now the biggest ones, the entire world electric grid has has the same power as what we have in these short bursts. But of course, he's really talking about energy. And that, on the grid, that power is happening all the time. And so the energy is coming all the time. And so if you wait long enough, there's more and more and more energy. Whereas in our short pulses, they're actually not very much energy. It's just that we've squeezed them to be very short pulses. And so if you shone it, either you could focus it down tight to have your hammer, but then you're going to blow up your solar panel, so that's not useful. You could shine it as a large beam on the solar panel, and you would create energy, but it wouldn't be much, because there's not that much energy in the laser pulse. And finally, he asked, can you put the energy back? Unfortunately, most lasers are less than 1% energy efficient. So for every joule you put out, you put 100 joules in or more. Now again, technology is changing, and we're using diode lasers, which are about 30% efficient and not 1% efficient. And those then drive the fiber lasers, which are about 90% efficient, but they're pumped by the diode laser. So altogether, you're still less than 30% efficient. So no, you can't take that and take it back into the laser.
It's a good idea, though.
It would be a good idea if it worked. But then that would be the perpetual energy machine too, and that doesn't work. Perpetual motion machine, no, doesn't work.
So I guess if we have just one more question, if you were speaking to a young science student looking ahead at the next 30 or 40 years of a career, what do you think are the most exciting questions to tackle, and what advice would you give?
Oh, well, there's so many questions out there, isn't there? I mean, and I can only talk about the physics ones, but obviously people love to consider astrophysics because we still don't know what most of space is, right? People would love to know what dark energy and dark matter really is. The quantum world wants to make that quantum computer, and so many people are excited about that. I still like lasers. I still like just seeing how light can change. You know, we see magical things. This is the beautiful thing about doing laser research, is that it happens before your very eyes. And one of my favorite things to show people is you can go in with the infrared laser beam, and just into tap water, every color of the rainbow comes out. And it apparently seems to come out of nothing. And you're looking at it, and you can watch it go in and come out. And it's like magic. It's one of the things I helped figure out when I was a postdoc. But even though I helped figure it out, when you watch it, it's still amazing to see. So there's so many fun things out there to think about and do.
That's wonderful. Well, I just want to say thank you so much to Dr. Strickland. This has been such a fascinating talk, and it's been a pleasure to learn about your work. Congratulations on the Nobel Prize.
Thank you.
And thank you so much to Dr. Hamdalapur and the whole University of Waterloo community for having us here tonight.
And thank you all for coming out on a very cold day. I appreciate that.
Yes. Thank you so much.